two spheres, identical mass, diameter, and material. And what's going to happen is one is going to be propelled, and I'm going to call it the y dimension. I say vertical, what I mean is up and down as you're looking at it, because actually it's horizontal. And an x dimension, which is left and right. So what I'm going to add to this is momentum arrows. This indicates the size and the direction of momentum, initially before the collision, and then for both balls after the collision. Now, as the mass is the same for both balls, the magnitude of momentum is directly proportional to its velocity. So up and down, which I'm calling vertical, my y direction, ball A has an initial momentum of m because of its mass, and u, and I'm going to use the suffix a for ball A and y for the y direction. Ball B is stationary, so it's got no momentum in the y direction. Horizontally, neither, or what we call the x direction, there's no component for either ball. The ball A is moving in the y direction only. So both the velocities, ubx and uax, are zero. That means there is no initial momentum in the x direction. Let's just watch that again. Okay, so the ball is moving up and down, but now when they collide, one ball sort of moves off to the left and ball A sort of to the right. So what we can see is before, and what I'm going to draw is a scaled momentum arrow. So this is the initial momentum. Then I'm going to look at the collision. This is just after the collision, and this allows me to get a track for where the next two balls go. And this is scaled final momentum. So this is based on taking a time period, looking at the distance, getting a velocity, and then scaling each arrow. Now, let's see what we can do with these arrows. Expand and putting the momentum arrows together. The red, P, is initial momentum. It's only ball A. And the two green ones represent ball B and ball A with final momentum. And I show them in green. Now let's not use what we call vector addition. And what this clearly shows, the vector combination of the final momentums equals the initial momentum, as they both have the same total momentum. This is an example of how we can show that momentum is conserved in 2 dimensions. Now we're going to look at a different method. And what I'm going to do is I'm going to take my final momentums and break them into y and x components. We can see them here. The y components, that's going in the direction up and down, are in yellow, and the x components, or left and right, are in blue. Now what we do is we add them up. Add them up vertically, or in the y direction, add them up horizontally. The vector components in both dimensions are equal, and it demonstrates that again, that we have conservation of momentum. If you look in the horizontal direction, vectors sum, and vectors are plus and negative. One is to the right, one is to the left. They are equal and opposite, and give me a final momentum in the x direction of 0, which is what the initial momentum was.